Welcome to the final lecture of week 3 for Math 320. Today we will give yet another example on how the least upper bound property can be used. We will in fact justify something that we all know pretty well, that real numbers have decimal expansions. To start with, let's quickly recall from the last lecture one of the variants of the Archimedean property, namely that given any real number x, there is a biggest integer that is smaller than x. That variant will play a central role in constructing the decimal expansion. Before we get going, since we will be using a lot of arguments using the Archimedean property, it is convenient to look only at positive numbers. So let us first explain how we can treat the non-positive numbers. If a number is 0, we declare its decimal expansion to be precisely 0. If a number is negative, we will use what we will discuss in the following slides to compute the decimal expansion of its absolute value, and say that the decimal expansion of a negative number is negative the decimal expansion of its absolute value. So, what is actually a decimal expansion? The great thing about mathematics is that you can frequently make your own working definitions, as long as you can say intelligent things about it and ideally connect it to things we already know from experience. So let me give you one such definition for positive real numbers. A decimal expansion is a way to specify an approximation of a real number. Here we assume to be positive. The approximation requires specifying a degree of accuracy, and that is the number of digits k. Here, the number of digits k, when compared to what we know well, refers to the number of digits behind the decimal point. A decimal expansion of the real number x with k digits is in fact a rational number formed by dividing some integer n by 10 to the power k. The integer n is chosen so that it is the largest integer less than 10 to the k times x. By the Archimedean property variant we talked about before, this means that for any number of digits k, there is in fact a way of specifying this integer n and hence the decimal expansion with k digits. Our description in the previous slide provides already a way to define the decimal expansion up to k digits for any degree of accuracy we want. What we will check now is that the decimal expansions are unambiguous. In particular, we will check that a real number x, positive of course by assumption, is uniquely defined by its decimal expansion. So, given a real number x, let's form its decimal expansion with k digits for each k, and call the resulting number x sub k. Let's collect all of these decimal expansion into a set, which we call d sub x. Notice that every element of d sub x is a rational number. Our theorem of this lecture is that the supremum of d sub x is equal to x. So we can reconstruct what a real number x is once we know its decimal expansion to arbitrary accuracy. Now, you may have seen something like this already in Calculus 2 when you talked about power series and geometric series. The neat thing about what we will be describing today is we are not using anything about sequences and series. In fact, in the next few weeks, we will repackage some of the ideas that are already present in today's discussion and use them to study the notion of sequences. But let's not get ahead of ourselves. Before we prove the theorem, we have to prove a preliminary lemma. Basically, one of the steps in the theorem requires a lengthier argument, and instead of trying to cram it on one slide, I will extract that lengthier argument into a separate slide and present it first. This lemma is yet another manifestation of the Archimedean property. It says that if x and y are real numbers that are both bigger than 1, then you can find a natural number n such that x to the power n is bigger than y. Remember, x to the power n is the n-fold product of x by itself. The x in this lemma has nothing to do with the x in the theorem on the previous slide, by the way. It is just a dummy variable. If you don't remember the main statement of the Archimedean property, please pause this video and dig up your usable statements sheet and read it over again. Okay, I assume at this point you either have the sheet in front of you or from memory you recalled what the main statement of the Archimedean property says. Do you see the similarity? In the main statement that we gave, the property is described in terms of the product n times x, or in other words, the n-fold sum of x with itself. In this statement, the property is described in terms of the n-fold product of x with itself. Otherwise, the two statements are extremely similar. So we expect the proofs to also be similar. And indeed, they are. Again, we assume for contradiction. Just like in the proof of the Archimedean property, that the conclusion of the lemma is false. That is, y is at least as large as any power of x. This means that if we take the set of S of all positive integer powers of x, this set has an upper bound y, and is thus bounded above. So to it, we can apply the least upper bound property. Remember, before using the least upper bound property, one of the hypotheses to be checked is that the set is bounded above. Call the least upper bound or supremum z. Since z divided by x is less than z, it cannot be an upper bound of the set S. So there must be an element of S that is larger than z over x. As elements of S are powers of x, we conclude that there is a natural power k such that x to the power k is larger than z over x. Rearranging this expression, we get that x to the power k plus 1 is greater than z. But since k plus 1 is also a natural, x to the k plus 1 is in S. This means that z cannot be an upper bound of S after all, and this contradicts step 3 where z is set to the supremum of S. So having reached the contradiction, our initial assumption is false, and hence y must be smaller than some power of x. Frequently, we want to apply the Archimedean property to get an integer that is larger than a given real number. This we can do directly using corollary 22 or proposition 27 if you still have the usable statements in front of you. But sometimes we want the number to be of a particular form. This lemma can be used to justify choosing your integer of the form 2 raised to the power k or 2 or 10 raised to the power k. Having proven the lemma, let's return to the theorem. Let's recall what we are trying to prove. We want to show that the supremum of the set of all decimal expansions with finitely many digits is equal to the real number x itself. Going back to how we define the decimal expansion, we saw that every element of d sub x is in fact less than x. So, this shows that x is an upper bound. We just need to show it is the least such. Returning to lecture 1, this means we have to show for any t less than x, t cannot be an upper bound. So let's just take an arbitrary t less than x. I claim that we can find some k such that 10 to the power k times the quantity x minus t is greater than 1. To find this k, what we do is first we use the Archimedean property against the positive number x minus t and 1 to find the natural number n so that n times the quantity x minus t is bigger than 1. Then we apply the useful lemma we just proved to guarantee that we can find a natural number k such that 10 to the power k is larger than n. So this means that 10 to the k times the quantity x minus t is greater than 1. Okay, with this application of the lemma done, we consider x sub k, the decimal expansion of x with k digits. This number we find to be bigger than t. This is because were x sub k less than or equal to t, the quantity 10 to the power k times x minus x sub k will be at least as large as 10 to the power k times x minus t. And so is also bigger than 1. Rearranging this, we see that this means 10 to the k times x sub k plus 1 is less than 10 to the k times x. But the definition of x sub k is that 10 to the k times x sub k is the largest integer less than 10 to the k times x. So we derived a contradiction. Please pause for a moment here and make sure you understand the reasoning behind step 3. The words given on the slide is a bit brief, and it is a mini proof by contradiction right there. Also, make sure that you understand how the chain of inequalities in the first line of the justification came about. From step 3, we're almost done. Since x sub k is in d sub x, step 3 shows that t cannot be a lower bound, which is exactly what we hope to achieve showing. So x is not only an upper bound of d sub x, but in fact its suprema. This shows the theorem. Alright, that's it for the material for this week. Before you go, let's quickly review what we have accomplished this week. We started by defining the concept of supremum and infimum. We took some time in lecture 1 to discuss how one can prove a number is the supremum of a set and how one can disprove a number from being the supremum of a set. In this lecture, we made use of the first part of that. We also discussed how supremum is related to maximum and also more general upper bounds. Hopefully, this gave you a better mental picture of these players and how they fit together. Another application was to discuss how suprema and infima of sets interact when we are given the knowledge of some ordering relation between the two sets. For example, if one set contains elements that are all smaller than the elements of another. In lecture 3, we proved several additional variants of the Archimedean property. These are all consequences of the least upper bound property, and each is a useful tool for analysis. And we showed as a consequence that the rationals are dense in the reals, in the sense that between any two real numbers, you can always find a rational interloper. And finally, in this lecture, we proved that real numbers have meaningful decimal expansions. With this, we have come full circle. We started this course by asking you to forget what you already know about the real numbers. We built up the real numbers by describing it as the enlargement of the set of the rational numbers so that it is order complete. Remember, completeness here is synonymous with having the least upper bound and greatest lower bound properties. With today's lecture, we've developed the theory so that decimal numbers again makes an appearance. Hopefully, you've gained the appreciation that our usual intuition regarding real numbers as numbers having decimal expansions is actually founded. That it is as a consequence of our understanding of the real numbers as something with the least upper bound property. With this, we end the first chapter of this course, which investigated the question, what are the real numbers? Starting next week, we will apply this understanding, specifically the least upper bound property, to understand things built from real numbers. First sequences, and then functions. See you next week.